All right, so you watched the last video and you said, oh my gosh, differential equations are so easy. This method rocks. I love separable differential equations. Well, this video is going to talk about sometimes things don't go so well. So what are the bad things that can happen? We're going to do this with examples, how I often teach a lot of things. So I want you to solve this differential equation, dy dt equals y squared. Also an autonomous solution, right? There's no independent variable in the right-hand side of the equation. So pause the video, solve it, see what you get. Go. What you should have gotten is -1 divided by t plus c. All right, pretty innocuous. That looks like a great general solution to this ordinary differential equation. This first order autonomous ordinary differential equation. Looks like a great general solution, and you can check your answer. This is correct. This is a correct answer. The problem is, well, what happens if I ask you to find the equilibrium solution? What's the equilibrium solution here? Well, the equilibrium solution is when the derivative equals 0. Well, that's when 0 equals y squared, which is when y equals 0. Well, the equilibrium solution is a solution, right? That makes the equation true. But that means this is not the general solution because this is missing one. Is it missing others? This method can miss solutions. So this is not the general solution to the differential equation, actually. This is the general solution. The general solution is both of these together. All right? So be very, very careful when looking at separable differential equations using this technique, is this technique can miss solutions. All right? Are there more? Let's look at another example. All right, so another example is solve this other differential equation, dy dt equals y over 1 plus y squared. To solve this one by hand, again, another autonomous ODE. To solve this one by hand, you're going to have to use a substitution. And you'll get some, well, I won't tell you what you're going to get. Pause the video right now. Try to solve this using our technique that we introduced in the last video. And what you should get is once you integrate both sides, you should find that the natural log of the absolute value of y plus y squared over 2 is equal to t plus c, which is great. That's correct. This is a general solution. Well, I think it's, again, missing an equilibrium solution of when y equals 0. But outside of that, right, this is a solution or a class of solutions to this differential equation. But you may have gotten a bit stumped here because how do you do this step? And that's the neat thing. You don't. Okay? So this is as far as you can go. And this is okay-ish. It's not going to make a lot, might not make you happy. But again, if we talk about like what can go wrong, right? We can miss solutions. Something else that can go wrong, right, is you can get stuck with only an implicit solution. And implicit solutions are okay, but yeah, we can't get an explicit solution. We can't solve this for y. All right. And again, this is still perfectly fine. Again, well, we're also kind of missing that equilibrium solution of y equals 0, I believe. And what else can go wrong? Let's do another example. I want you to get more practice with this. What if you solve this differential equation, y dot equals the secant of y squared? Again, another autonomous ODE. Well, pretty quickly on this one, pretty quickly what you're going to get, well, we can do this one together, right? Y dot is another way of writing dy dt. We divide both sides, we multiply by cosine of y squared is the same as dividing by secant of y squared. And we're going to get cosine of y squared dy. When you divide it out, you're just left with 1 dt. I can integrate the right-hand side, no problem. I cannot integrate the left-hand side, and I'm a math professor. Can you integrate the left-hand side? Probably not. The left-hand side is an example of an integral that doesn't have an elementary antiderivative. Okay. Now, if there were a y right here, we could do a substitution and we'd be really happy. So there are many integrals, right, that have no elementary antiderivatives. And so you can run into this as a problem as well when you're solving differential equations with this method. So a few things that can go wrong. But again, the good news is, and this is one of the things that I love how our textbook really organizes things, is analytic solutions are not the be-all end-all, right? We talked about how with this specific analytic method, to find exact solutions to our method, we can miss solutions. We can be stuck with an implicit solution and can't get an explicit. And sometimes we can't get a solution at all because there's no elementary antiderivatives for what we need. But remember, analytic solutions are not the be-all end-all of differential equations. In fact, most differential equations go to the other methods. Remember, there's 3 things that we always talk about. Analytic solutions, qualitative analysis, and numerical approximations. So the next section, I believe it's the next section, we talk about slope fields, which let us get more qualitative analysis. And then we'll later talk about an example of a numerical method as well to get approximations when we can't solve things by hand. So the good news is, right, analytic solutions, doing math by hand is really, that's a calculus problem. We're going to be doing a lot of other things, and especially when you get to partial differential equations, nobody's really doing most partial differential equations by hand either. So good news and bad news. This is what can go wrong with this method. But yeah, it's just a lot of integrating. You can check your answer with derivatives. In the last video, we're going to do something exciting, and we're going to introduce a mixing problem, a nice application problem with fun stuff in it. So that'll be how we conclude this section. Bye-bye.